So we have a 300 ohm resistor on the top. We have a voltage source here of 150 volts. We have a switch here that is actually open, but at t equals to 0 closes. We have nothing here actually. There's no resistor here. I started to put another one, but let's go with nothing. Let me just erase that. So there's really nothing here, just attached to it. Now we have an inductor of 5 millihenry here. And we have a resistor of 200 ohm here. Then we got a capacitor of 20 nanofarad. Nanos 10 to what power? -9. And let's say what the question here, I don't know, find the voltage across the capacitor, VC, as a function of time. VC, the voltage across the capacitor, right here. And notice here we have, this is the first time we're hitting this, we have capacitor, resistor, and inductor. That's why it's called RLC. You have a resistor, inductor, and capacitor in them. So anytime you have an RLC circuit, you will end up with a second order differential equation. So you're going to end up, it doesn't matter what you're solving for, you're going to end up with the second order differential equation. What does that mean? You're going to have a differential equation that will look like this. I'm going to put a special format for it. I'm going to call this 2 times alpha plus, I'm going to call this W here, now notice as I close the switch, I'm not going to have a source in this. That's called source-free circuit, so this will be a 0. But if I have another source, this will not be a 0. They'll have a forcing value, forcing function. We'll deal with that later. So if you end up with an equation like this, I'm not going to go through the math how to solve it, but there are 3 options. It depends if alpha is greater than W. That's called overdamped. If that's the case, the solution here will look like this. It's some constant, we'll call it K1. We'll find what K1 ought later. E to the power of negative alpha plus the square root of alpha squared minus W squared times T plus K2 e to the power of negative alpha minus the square root of alpha squared minus W squared T. If alpha equals W, that's called critically damped when we get to it, then your solution for that equation is going to be K1 e to the minus alpha T plus K2 T e to the minus alpha T. And if alpha is greater than W, that's, oh, I have them backward, yeah, less than W. That's greater than, that's less than here. Can't be both the same, right? That's underdamped. Then the solution will be e to the minus alpha T times K1 cosine, because W is bigger than alpha now, the square root of W squared minus alpha squared T plus K2 sine W squared minus alpha squared T. That's what the three cases are. So I have to look and see, is alpha bigger than W? Is alpha less than W? Is alpha equal to W? And based on that, that will determine my answer. But again, you can cover that in differential equation, how to solve this one. I'm just telling you that's how I'm going to do them. I'm going to find what alpha is, what W from my equation, and based on that, I go, there's my answer. So let's look at this problem. I got to look at lots of things in this problem. This will be like a 3-4 page problem. First thing I need to do is look at it for t less than 0. That's the first thing. So t less than 0. The switch is open. That means I have a source. I have a DC source. And to DC, if you remember, we said the capacitor will behave as what? An open circuit. The inductor behaves as what? Short circuit. So we have a DC source. Which means the capacitor is going to be treated as open circuit. And the inductor will be treated as what? Short circuit. God, I hate this pen here. And the reason I'm looking at the circuit for t less than 0 because I need to find the current through the inductor as 0 minus, and I also need to find the voltage across the capacitor as 0 minus. So that's step number 1. Look at the circuit for t less than 0 and find, that's a comma there, find both of these. So let's look at it. Here's my circuit. There's the 300 plus to minus 150. This is going to be a short circuit. This is the 200. And this is going to be an open circuit. So I sub L is the current. This is I sub L as 0 minus. I'm looking for it. And this is VC as 0 minus right there. Oh, can't see him, but that's what we're looking at.
How come you made it going down? Or you just...
Well, good question, because I'm labeling this as VC, right?
Yeah.
So these, I'm looking at the circuit already. I'm looking ahead for t greater than 0, because it's going to be like this, right? So the voltage is going to be plus on the top. That means the current is going to be coming down. So might as well find that current instead of going up there. So I kind of cheated, but that's a good question, actually. I can find VC here by voltage division, right? VC will be what? A 0 minus will be the 150 voltage division times the 200 divided by the sum of these two resistors, which is what? 500. Bless you. Is that 60? And can I find the current I sub L is 0 minus? Well, notice here, minus to plus, the source is actually the current going to be traveling this way. Bless you. So my current here is going to be what? Negative. Everyone see why it's negative? It's going to be traveling because of the source minus to plus. The source is going to supply the power. It's going to travel this way. So it's going to be negative 150 Ohm's law over the sum of the resistor, which is what? 500. And what do we got? 0.3 is it? With a negative sign. I think it's 0.3.
It's like 332.
Is it? Yeah. That's 0.3. 150 over 15. I mean 500. It is 0.3. Yeah. So it's a negative because it's coming back. So I get the two things that I need. Look at the circuit for t less than 0, calculate the current through the inductor, and calculate the voltage. The reason I'm looking for these because I know the voltage across the capacitor now is 0 plus, is really does not change, is the same as 0 minus, which is going to be 60 volts. And the current through the inductor as 0 plus is the same as the current through the inductor 0 minus, which is negative 0.3 amps. So that's the first step. Now, step number 2, I'm going to look at the circuit for t greater than 0. And I need to write a second order differential equation. Differential equation. So look at the circuit for t greater than 0 and write a second order differential equation. The switch is going to close. So if I close that switch, here's what I'm going to have. Five millihenry. That's 200. And that's the 20 nanofarad. And this is VC. Actually, all the top is VC if you want to. Like this. Now, if you want to actually do a KCL here, this can be treated as a super node. But what you're going to find out, this way you're not going to have any effect on this one. There's a current coming down here. Anyone knows what that current is? If this is VC, what's this voltage here?
VC plus 150.
Yes, VC plus 150. So there's a current going down this way, and that current is going to equal to what? 150, VC plus 150 minus VC, which is just 150 over 300. Is that 0.5? I think it's 0.5. Or 0.6, I think. Is it?
No, it's
0.5? Yeah, it is 0.5. Well, where's that current coming from? That current better be coming up from here. This is also 0.5. So if you do KCL at right here, VC, KCL at VC, I don't know, I said VC, VC, right there. Assign current. This is I sub L. This is I sub R. This is I sub C. The current entering the node, if you add all the current entering the node, should equal all the current leaving that node. What is entering that node? The 0.5 amps, right? It's coming to it. I'm not even treating this as super node. What's leaving that node? The 0.5 plus I sub L plus I sub R plus I sub C. And what do you notice about that 0.5 and 0.5? They cancel each other out. Same current. So that's why you can look at the circuit just like this. If you just treat it just like that, you go KCL of this node, what's going to it? Nothing. What's leaving? I sub L plus I sub R plus I sub C. Isn't that the same thing?
And we know I sub L is negative 0.3.
Well, no, that's a 0 minus. So I want to find at any given time.
Okay.
Now, if you remember, let me just refresh your memory. For an inductor, it's L di dt, which means I sub L is equal what? 1 over L, the integral from negative infinity to t of v dt. V of t here, dt. Capacitor, this is the inductor. Capacitor, I equals C dVc dt, which means Vc equals what? 1 over C, the integral of negative infinity to t of I sub C as a function of time dt. So those are the equations I'm going to be using. Let's find the current through the inductor. Where is the current through the inductor? Based on that equation, the current through the inductor is what? 1 over L, the integral from negative infinity to t. And what is the voltage across that inductor? Isn't that Vc? The three of them are in parallel. They have the same voltage. What's the current through the resistor? Well, that's this voltage divided by 200. What's that voltage cross? Vc divided by 200. And what's the current through that capacitor? I equals what? C dVc dt. Now notice we have an equation that has an integral and a derivative. And to get rid of the integral, what do?
Take the derivative.
We take the derivative of the whole equation. The derivative of 0 is what? 0. The derivative of the integral, they cancel each other out. 1 over L, the voltage across the capacitor. This is actually 1 over R here. Instead of it, I'll just use R for now, because R is the 200. 1 over R, the derivative of that, and this will be C times the second derivative. Now, if I divide everything by C and reshuffle everything, divide by C and reshuffle everything, I will have the second derivative (1 over RC) plus 1 over LC equals to 0. Now let's plug in the values. (1 over RC). What was R for that problem? R is 200 and C is what? 20 nano, 10 to the minus 9. Let's see what that number. 1 divided by parentheses 200 times, is it 20 or 20 nano, times 20 EE to the negative 9. And I got here 250,000 dVc dt plus 1 over LC. 1 divided by L is what? 5 milli? Was it 5 milli? 5 million 20 nano. 5 EE to the negative 3 times 20 EE to the negative 9. That's 1 times 10 to the power of 10. Now, if I compare that to my equation, what I started, I said, I'm trying to write a second order differential equation from the first thing I did. I said, my second order differential equation is going to have that format. And I call this one 2 alpha. And I call this W squared. So when you compare the two of them, when you look at them, this is your 2 alpha. So my 2 alpha has to equal 250,000, which means alpha will be what, 125,000? And when you compare this one, this should equal to what? W squared. What's W? Isn't that half of that? 10 to the 5, which is what? Is that 100,000? So who is bigger, alpha or W?
Alpha.
Alpha is larger than W. Since alpha is larger than W, based on what I wrote there, my solution for this equation, now the derivative, the voltage across the capacitor as a function of time should be some K1 e to the power of negative alpha. Alpha is 125,000 plus 125,000 squared minus 100,000 squared plus K2 e to the power of negative 125,000 minus 125,000 squared minus 100,000 squared. If I do the math, that looks ugly, but if I do the math, these will be normal numbers. Let's see, what's 125,000 squared minus 100,000 squared. Take the square root of that number. That's 75,000. So it's going to be K1 e to the negative 125,000 plus 75,000 T. And the other one, K2 e to the negative 125,000 minus 75,000 T. What's the voltage now as a function of time? It's K1 e to the what? Is that negative 50,000? Plus K2 e to the power of negative 200,000.
We can't see.
Yep. That's my voltage now. So I wrote the differential equation, and I got all the answers to it.
Don't you need plus K3?
Well, no, I don't have a constant here.
Oh.
Notice K3 if there is a forcing function, if this was here like a 5 or a 7 or a 9, then I need a forcing value. I need K3. When it's 0, there is no K3. Oh. I'll bring that next time, next example.
How do we find that?
Yep, good question. The question is, how do we find K1, K2?
You gotta look at the time.
So how many unknowns do you have here? That's what step number 3 actually is. We know what the voltage at 0 plus is. We did that earlier. That's the first step. Where is it? Step number 1. I look at the circuit for t less than 0 and find the voltage across the capacitor as 0 minus, which is the same as 0 plus. We know that's 60. So let's see. I need 2 equations by 2, and I know the voltage across the capacitor is 0 plus. That's equal to 60. Let's plug in t equals 0 plus. So I will have K1 e to the what? 0 plus K2 e to what power? 0. So I have 60 equals what? K1 plus K2. That still doesn't help me. That's one equation by how many unknowns? 2. I need another one. I need the second equation. Okay. Let's go back. That's step number. So let's go back. Look at the circuit at t equals 0 plus. At that time, right there. Let's look at the bottom half of the circuit. Talk about this half here. Let's look at that. This is what we have. Uh-oh, come back here. We have what, 5 millihenry here? We have what, 200 here? And we have the capacitor here, which is what, 20 nanofarad? And at that time, at t equals 0 plus, we know the voltage across the capacitor was what? Wasn't that 60? That means the voltage here, then parallel, at that time must be 60. We also know the current coming down here at that time. That's from t less than 0. What was the current coming down at that time? Negative 0.3, right? That doesn't change. You agree with all that stuff? That's from t less than 0. We know the voltage across the capacitor is 0 plus is 60. The current through the inductor is 0 plus is also negative 0.3. We calculated those. That means I know what the current down here is going to be at that time. We know the voltage, we know the resistor. What's 60 divided by 200? Is that 0.6, I think? Or is it? 60 divided by 0.3 maybe. That's 0.3. Let's do KCL right here. Let's call this current I sub C. So I sub R plus I sub L plus I sub C is equal to 0. What is the current through that resistor coming down? We said that's 0.3 at that time, at t equals 0 plus. What's the current through the inductor coming down? Negative 0.3. What's the current through the capacitor? I equals what? C dVc dt. This is the voltage at 0 plus. We're looking at that time. if you do your math, these two will cancel each other out. You end up with the derivative of the voltage at 0 plus is equal to what? 0. How is that going to help me? Let me go back a previous page. We found the voltage across the capacitor at t equals 0, right? Let's take the derivative of that. Do the math. What's the derivative of the voltage at any given time? I'm not saying at 0 yet. At any given time. What's the derivative of that equation? Isn't that negative 50,000 K1 e to the what? Negative 50,000 t. This will be a minus 200,000 K2 e to the negative 200,000 t. That's the derivative. So what is the derivative at 0? Let x be 0. We know from the circuit the answer was what? 0 from the circuit. But what is it from the math, from here? Isn't that e to the 0, which is a 1? Negative 50,000 K1 minus what? 200,000 K2? And that's my second equation. Now I got two equations by two unknowns to find K1 and K2. So I looked at the circuit at t equals 0 plus, calculated the change in the voltage at that time from the circuit. I also did it from the equation, and it should be the same number. So I have two equations by two unknowns. This is one equation, there's the second one. Let's solve them. Let me write the two equations. The first one says K1 plus K2 equals 60. The second one says negative 50,000 K1 minus 200,000 K2 is equal to 0. I'll solve this by hand because I get a lot of questions. Can you please show the math when you solve these equations? Never mind using your calculator there. Well, you can multiply this equation by what? 50,000. Use the elimination method. So you have a 50,000 K1 plus 50,000, well, that'll be, yeah, K2 equals what's 50,000 times this? That'll be, is that 300,000? Add them. Negative 150,000. K2 equals what? 300,000. What's K2 is going to be?
Isn't that 3 million?
1, 2, 3, 4, 5. And 6 times 5 is 30. You're right, 3 million. Where's my whiteout? Oh, down there. On the. So that'll be a negative. I can drop 3 zeros here. 3 million or 3,000 now over 150. 3,000 divided by 150, 20. So K1 plus K2 is 60. What's K1 then? Does it have to be 80? 80 plus a negative 20, is that a 60? Yep. So now what's the voltage across the capacitor at any given time? It's going to be K1, which is 80 e to the power of negative, was it 50,000? can't remember, 50,000 t minus 20 e to the power of negative 200,000 t. That's for t greater than 0. As I said, these problems are lengthy. Take us a while to do them. Sometimes our book managed to do them in about 15 seconds. I'm not that talented. I can't do them in 15 seconds.
That's only for t greater than 0?
Yep. Well, for t less than 0, we know what that is.
Oh, yeah.
We already did that, right? 60. So you just got to graph that function, see what the graph looks like for that function.
Do you think we'll have something like this on the exam?
Oh, definitely. That's the biggest thing. Now, let's look at it when alpha, for example, equals, let me try a different example. Maybe I'll pick one when alpha equals w there. We might have time to do that. Let's see. Let's take another example. We got, what, 17 minutes? Good luck. So the way this one is set up, this problem is written like this. Select the value for R. So, this is actually not solving it. Let me see if I can find something in the back or. Let me go to the back of the book and see if I can pick a problem. For the circuit, determine. Okay. There is a problem. They're asking us to find 10,000 things, but that's okay. We have a current source. They're asking for the current through each one for t less than 0, greater than 0, z plus 0 minus, all the stuff. You have 3u of negative t. We get 2.5 microfarad capacitor here. We have a resistor of 2 ohm right here. There's a switch in parallel with that. And the switch is open right now, but closes at t equals to 0, which means for t greater than 0, that resistor is gone. We have an inductor here of 20 millihenry. Then we have a resistor of 50 ohms at the end of that. And I have no idea what's going to happen here. I'm hoping alpha will not be greater than w here, because I want a different example. We did this one, so I'm optimistic it's either going to be this or that. I won't know until I do the math. Try to do a quick shortcut in my head there. I will have to say probably somewhere there, because I took this from the back of the book. Now notice this is 3u of negative t. In case you forgot u of negative t, u sub negative t has a value of 1 till t equals to 0, then it goes to 0. That's u of negative t, not a plus t. So it has a value of 1 for t, that's just the u sub negative t, has a value of 1 for t less than 0. then it has a value of 0 for t greater than 0.
What's the value of the resistor, the rightmost resistor?
This one?
Yeah.
50 ohms.
Okay. I thought that was like negative.
No, I'll make that out. That's a 50 ohm. So let's look at the circuit again. For t less than 0, that means this guy was cooking, it was working, has a value of what? 3 amps. What is the capacitor going to behave as? I'm looking for VC again, by the way. That's a DC source. What's the capacitor going to look like? Open circuit. There's that resistor of 2. There's that inductor. And this is the current through the inductor, I sub L. That switch is open, so it's going through it, and there's the 50. That's what my circuit's going to look like. I defined the current coming down. I could define it going up. It's not a big deal, by the way, which way we define it. But I'm trying to anticipate what's going to happen next. But you could define any direction. Now, what is I sub L at 0 minus? Well, that's current division. This is nothing. Nothing's going to go through that. So this and that is going to be the 3 amps times the 50 over the 52. Is that a 2 or 20? That's a 2 and that's a 50. Okay. So what do we have? 150 over 52? Forgot to do. Huh? 3 times 50 is 150, right? Divided by 52. 2.88. Now keep in mind these 3 or 4 are in parallel. The capacitor is gone, but this, and the capacitor and this are in parallel. So I know the voltage across this, which is the same voltage right there. So the voltage across the capacitor is 0 minus is going to be 2 times I sub L. So times the 2, and that'll be 5.77 roughly. So that's the whole idea of looking at the circuit for t less than 0. Can I find these two numbers? Because those will be the same for the current through the inductor 0 plus, and the voltage across the capacitor 0 plus. They don't change in 0 time. Now I need to look at the circuit for t greater than 0. Keep this one handy, I'll need it. What's going to happen to that resistor? That switch will come down, that will short circuit that. That's gone. What's going to happen to this current source? Is going to be what? 0. That's gone. So that current source is gone because it goes to 0. And when a current source goes to 0, that's an open circuit, so it's not even there. So what you have is the capacitor now of 2.5 microfarad. That resistor is short-circuited here, it's gone. You have only the inductor at 20 millihenry.
And the resistor.
And you get that resistor at the end, the 50.
What about the 2?
That's short-circuited.
Oh.
The switch closed at t equals to 0. Gone. 0 in parallel with 2. The product over the sum. And this is VC. So I'm going to define current coming down because the voltage is plus on the top. That's I sub C, I sub L, I sub R. KCL says all the current entering the node equals all the current leaving that node. Leaving is nothing. Here we go. I equals C dVc dt. In case you forgot, we said that, what is it? I wrote it down somewhere. Right here. The current through the inductor, 1 over L the integral. 1 over L the integral of d dt. So that would be 1 over L the voltage cross, that happens to be the voltage cross the capacitor, and the current through that, which is the voltage right here, which is the voltage cross the capacitor divided by R. Again, if you take that equation, take the derivative of it and divide by C in one step. If you take the derivative and divide by C, you end up with the second derivative plus 1 over RC, the derivative of this, plus 1 over LC, now, the reason our book does it really quickly, I'll tell you what they do. They don't even write the equation. They look at the circuit. If they see capacitor, inductor, and resistor, they know there's your answer. There's your differential equation. So they don't do any of the steps I did. They just go to that equation. They just plug in the numbers. So here we go. That's squared here. R is what? 50. C is 2.5 micro, 1 over that. Here we go. 1 divided by parentheses 50 times 2.5 EE to the negative 6. And I got 8,000. One over LC, 1 divided parentheses L, 20 millihenry, times C, 2.5 micro. God, I got a lot of zeros here. 1, 2, 3, 4, 5, 6. I think 20 million. Meg, I think. Is that what you got, 20 million? So when you compare it to my equation, that's your 2 alpha. That's your what? W squared. So what's alpha equal to? 4,000. And what's W equal to? The square root of that number. 4472. And some change, but that's fine. So this is 2 alpha, and that's W squared. That tells me which equation to use. Alpha is less than W. Since alpha is less than W, the voltage across the capacitor based on my solution, here we go. When alpha is less than W, e to the minus alpha, e to the minus 4,000 t times K1 cosine W squared minus alpha squared. We'll do that later. plus K2 sine W squared minus alpha squared T. Let's see what that number is. That's 2,000 when you do the math. So it's e to the negative 4,000 t times k1 cosine 2,000 t plus k2 sine 2,000 t. That's the voltage across the capacitor. Step number 3. So what do? We did step number 1, look at the circuit for t less than 0. Step number 2, look at the circuit for t greater than 0 and find out what the solution is. Step number 3 is what? Find K1 and K2. I can get one of them. I know the voltage across the capacitor is 0 plus. We did the math. What was it? 2.88 was it? No. 5.77, wasn't it? That's equal e to the 0, k1 cosine 0, plus k2 sine 0. E to the 0 is 1, sine of 0 is 0, cosine of 0 is 1. What's k1? I'm making progress. I know what K1. So I know now the voltage across the capacitor at T here. K1 is 5.77 cosine 2,000 T plus K2 sine 2,000 T. Getting close to it, really close. I just need K2. So if this is a 10-point problem, probably got 7 points already. I got the equation, I got K1, I got the initial conditions. I just get that K2, the 3 points, I need that. So that's when we look at the circuit at t equals 0 plus. We look at the circuit and we look at the equation, the derivative. So that's step 4 basically. Let's look at the circuit. At t equals 0 plus, this is what my circuit looks like. This is the 50. This is the inductor. And this is the capacitor. They're not zeros, they're not open. After a while they become. We said the voltage across the capacitor 0 plus is what? 5.77? And since the 3 of them are in parallel, I know this current now. That current has to be 5.77 divided by what? Oh, no, sorry, not that one, this one. 5.77 divided by 50. 0.1154. I know the current through the inductor is 0 minus. We did the math. What was the current through the inductor is 0 minus? 2.88. So if I do KCL, this is I sub C. We're not sure what I sub C is. As 0 plus, I say, okay, 0 equals I sub C plus I sub L plus I sub R. I equals C dVc dt as 0 plus. I sub L as 0 plus is what? 2.88. I sub R is 0 plus 0.1154. Add these two numbers together. It's negative 2.9954 equals C dVc dt. Now divide by C. C is 2.5 micro. I came up with some big number. Did you get that number? 1198,160. Hopefully that math is good there. I don't trust my math skills on the calculator there. And now I need to find the derivative from the equation, then I'm done. So this is the derivative from the circuit. Let's go to the equation, take the derivative. Oh, let's test your calculus skills. How do you take the derivative of this? What method would you use? Is that the same number? What method would you use here? Take the derivative. Product rule, yes. Remember you have a multiplications. So what's the derivative now? The product rule. So it's the first, which is e to the negative 4,000t, times the derivative, that's 2,000 here. What's the derivative of that? That's 2,000 times this, that'll be a minus. Derivative cosine's negative sign. 5.77 times 2,000. 11,540 sine 2,000t plus 2,000 K2 cosine 2,000t plus the first times the derivative of the second plus the second cosine 2,000t plus K2 sine 2,000t times the derivative of this, which is negative 4,000 e to the negative 4,000t. Instead of trying to simplify it right now, imagine it might be easier if we look at it t equals 0 plus. At t equals 0, this will be e to the 0, which is what? 1. What's sine of 0? Gone. What's cosine of 0? 1. That will be 2,000 K2 plus cosine of 0 is 1. That will be what? 5.77. Right? Just 5.77 plus this will be 0 times negative 4,000. So if we multiply that, this will be negative 23,080, I'm almost done, plus 2,000 K2 should equal the derivative. What was the derivative from the circuit? Where is that equation? Wasn't the derivative equal to this? Let's plug in that number. Negative 11,98160. And now I'm done. to remember which equation, which one is 1, 2, 3. I can't even tell. So now I should be able to solve for K2. That would be negative 1175,080. Double check the math. What's K2 equal to? I got 586, 587.5. How about 588? It's good enough. And I'm
Negative?
yes. And I'm done. I know what the solution to that equation now. I know what the voltage across the capacitor. I was waiting to find K2, right? Now I go back to this, the voltage across the capacitor at any given time for t greater than 0, it's e to the negative 4,000 t times 5.77 cosine 2,000 t minus 588 sine 2,000 t for t greater than 0. Hallelujah. Woo! Couple more examples next class, and we done.